Well, hello, my name is Ian, and today I'm going to talk about how to analyze piping and instrumentation diagrams. Well, first of all, I would like to start by introducing briefly some background and key concepts of P&IDs. Well, P&ID stands for Piping and Instrumentation Diagram. It is also known as a MFD, which means Mechanical Fluid Diagram. This diagram could be explained as an improved version of PFD, which means Process Flow Diagram, uh, which it is also an improved or more specified version of a BFD, which means block flow diagram. Well, these three diagrams or ways of representing a process, they are all the three of them are good. No one is better than the other one. It just depends on how much information you want to give or explain, or who you're explaining to. Well, a piping and instrumentation diagram provides information needed by engineers to begin the planning and construction of the plant. The P&ID includes every mechanical aspect needed by engineers in charge of the process. Its main use and importance. Well, a P&ID is the last stage of the design of any plant, so it can be useful for its maintenance in the future, as well as a process recognition once the plant is functioning. Uh, Well, the main uses for a P&ID are maintenance and equipment. Well, as we can see, the whole operation that occur on our process, we need the information of every one of the equipment to know what's happening, such as calibration periods, maintenance needs and dates, and all the information sheets for each equipment. The programming controls. Once we have the P&ID, we can recognize the needed inputs and outputs of the streams. For example, temperature needs, pressure, or level needs as well. We can implement a PID or any other control device more easily if we have this diagram in order to make our production more efficient. Well, we can work on improvements for the process when we have the diagram. We can make standardization of activities. Safety issues. Well, with the diagram, we can recognize what is needed for a more safe operations, as well as the parts of the process that need to have more strict implementation of safety procedures. Well, obviously, when we complete the P&ID, we can know what equipment, piping, valves, etc. we need for our operation to work, and therefore how much money we will need to invest or to use for maintenance and repairs. Well, finally, the operational information, which the P&ID, we can have the operational information available whenever we need it. Well, this is an example of a piping and instrumentation diagram for benzene distillation. Well, in this diagram, we can recognize all the instrumentation needed for the equipment to work properly. For example, the temperature systems that control the distillation tower, or the level systems to control the vessels in, well, as we can see in V104, or in here in E104. Where we can see another temperature arrangement for this heat exchanger. Well, these systems that control inputs and output signals are crucial in chemical processes to make the operations easier to control, well, more safe, of course, and consequently having a better functioning. Symbology. Well, we have some symbols used as a standardization for all P&IDs. Used in chemical processes, or actually every process. This is done so that every chemical engineer or every engineer who runs the plants can understand the diagram. For example, let's say that a process engineer of our organization gets fired and we need a new engineer. So he arrives, and if we do not have a correct symbology in our P&ID, well, the new engineer will not be able to understand it, and this could be a very big and important problem if anything goes wrong, for example. Well, on the left part of this table, we can see the signals that are more important to control, for example, level, temperature, pressure. And well, the complement letters are, for example, controllers, transmitters. Well, I will give a more mm, detailed example further in the presentation. Now, the part that we want to know, how to analyze a P&ID. Well, now that we know that what a P&ID is and that its main functions are monitoring and troubleshooting, we can proceed to analyze one of these diagrams. Well, first of all, we need to know that they provided the following information: the identification of components within the diagram, how the instrumentation and equipment is connected, and their location in the process, and also their function in the operation. It would be very difficult to analyze a whole diagram with a different equipment at once, so it is better to start with a single process and so on. For example, in here that we have a lot of processes, like, I don't know, a heat exchanger, a distillation tower, a reactor, a vessel, etc. If we try to analyze a whole diagram as a whole, it would be a very difficult activity, and we could be messing up, I don't know, the recognition, or messing up the control systems, or whatever. It is better to start with a single process and go on from there. For example, in here, this is an example of a very common one, but it will illustrate perfectly what a P&ID is. Well, in here we have a little part of a process to show an example on how the analyze works. We are looking at a tank or vessel with a level control loop. We can know that the level is the signal in control because of the letter L at the beginning of the balloons, which specifies a measure variable in every P&ID, in the left letter, as we can see on the symbology that I showed earlier. With the letters LV only indicates the type of valve we are working with. I mean, the V on the balloons always indicates that it's a valve, and the L, the signal. The letter C indicates it's a controller, and the letter C indicates it's a transmitter. Well, a dashed line between the components always indicates an electrical signal, which is part of the control loop. On the other hand, a line with the diagonal marks designates a pneumatic connection, which regulates the level with a physical action. In this case, it is a pneumatic control diaphragm actuator, which opens and closes the valve, regulating the fluid. Well, this is a little example that can be very useful. Well, here are some references for further investigation.